As a general pattern, note that for the prediction problem, usually we are interested in finding V of S, which is what we just did. For the control problem, we are usually interested in working with the action value, Q of SA. The reason for this is, if you recall, the Q function makes it easy to look up what action to take given a state S. We always take the argmax over all possible actions. We call this the greedy action. In this way, we maximize what we believe to be the sum of future rewards. So just keep this general pattern in mind. For the prediction problem, we work with V of S. For the control problem, we work with Q of SA. In order to understand how to apply the Monte Carlo approach to the control problem, we first have to understand the principle of policy iteration and policy improvement. Let's consider two basic facts. Number one, given a policy, we can use Monte Carlo to evaluate the value function, whether that be the state value or the action value. We just saw that in the previous lecture. Number two, given an action value function, we can always choose, based on this, what we believe to be the best action given the current state. This is just the argmax over all possible actions A. Well, it turns out that these two facts are interdependent. Given a policy, we can find its corresponding action value, and from that, we can take the argmax to find a possibly better policy. But what if this policy is different from the original policy? Then we can find the value function for this new policy. And from that, we can take the argmax again to find yet another new and possibly better, but at least as good, policy. From there, we can find the value function again. So you see, this is just a loop where we go back and forth, finding the value function given a policy and improving the policy given that value function. You can see that we have named these two steps. The act of finding the value function is called the evaluation step, and the act of finding the best policy given that value function is called the improvement step. And just to be clear, the reason why this is a loop is because they both change each other. So by doing step 1, you change the policy, and by doing step 2, you change the value. It's been proven, although we won't discuss it here, that performing these steps leads to a monotonic improvement in the policy. Therefore, if we just keep doing this process, eventually we will end up at the optimal policy. So how can we apply this to Monte Carlo? Here's a rough outline. First, we start by initializing Q of SA and our policy to both be random. Next, we enter a loop that goes for a predetermined number of episodes. Inside the loop, we first evaluate the policy by finding Q of SA for the given policy. We call this the policy evaluation step. Once we've done that, we find a new policy where, for each state, we take the action to be the argmax over all actions for Q of SA with a given state. This is called the policy improvement step. This is pretty simple and not unlike the prediction problem, except for one small difference. Note that earlier, when we discussed the evaluation problem, we discussed how to find V of S. But now we have to find a Q of SA. In order to find Q of SA, where we evaluate our policy, we need to keep track of not only the states and rewards, but also the actions. So we're going to record triples of states, actions, and rewards. So S1, A1, R1, S2, A2, R2, and so on. Here's what the pseudocode for the evaluation step would look like. As you can see, this is pretty similar to calculating V of S, except when we store the sample returns, we index the dictionary by both state and action. In the second part, Q is again a dictionary, but now the key is a state action tuple. Other than that, the process is exactly the same. We still calculate the sample mean of each list of returns for a given key. At this point, our solution works, but it's not an ideal solution. Let's think about why. First, if you recall, V of S only stores big S values, but Q of SA stores big S times big A values. As you know, with Monte Carlo sampling, the more samples you collect, the more accurate your answer becomes. When we use Q of SA, we have many more values to estimate, and therefore, we have to collect many more samples in order to get an accurate estimate. But there is a second problem. Each policy evaluation step is a Monte Carlo estimation, which means that we must calculate a large number of samples. But now we've nested this loop inside another loop. What's the effect of this? Well, let's say our policy iteration loop needs to run 1,000 times to find the optimal policy. Now let's say our inner loop needs to run 1,000 times in order to get an accurate estimate of Q of SNA. How many episodes do we have to play? The answer is 1,000 times 1,000, which is 1 million. As you can see, our data usage is not efficient, and the number of times we need to play the game grows quite fast. A better solution is to use what's called value iteration. At first, this approach may seem kind of wacky, but in fact it's been shown to work. The idea is this. For the policy evaluation step, instead of playing multiple episodes in order to get a good estimate of the value of our policy, we are only going to play one episode. After playing this one episode, we'll get a series of states, actions, and rewards from which we can calculate the corresponding returns. From that, we can loop through each state, action, and return and use the latest sample of the return to update Q of SNA. Now you'll notice that I've just put some pseudocode here, update Q of SNA, but I haven't told you exactly how we're going to do that. We'll be discussing this shortly. The important thing to note right now is that we'll only keep a single running copy of Q of SNA. The next and final step is the same as before. We update the policy by taking the argmax over Q for a given state over all actions. So what's going on with this line here? How do we update Q of SNA, given the old estimate of Q of SNA? For this, we need to take a short digression back to sample means and expected values yet again. As I'm sure you're tired of me repeating by now, this is the expression for the sample mean. We sum up all the samples and we divide by the total number of samples. The question we have to ask is this an efficient calculation? The answer is no. Summing up n values is O of n. The more values we store, the more time it takes to calculate. This is not good. So the question becomes, is there a way to reduce the time it takes to calculate the sample mean every time I collect a new sample? To see how this is done, let's express the sample mean in terms of the previous sample mean and the latest sample. Before we move on, please make sure you can derive this yourself on paper. In the derivation you see here, x bar n means the sample mean using the first n samples. Thus, x bar n minus 1 means the sample mean using the first n minus 1 samples. The trick is, we can turn the above expression into something that looks like, and in fact is, gradient descent. We can write it so it looks a little more familiar. The new estimate is equal to the old estimate plus 1 over n times the nth sample minus the old estimate. In this scenario, the target is the latest sample we've collected, while the old estimate is our prediction. 1 over n is the learning rate, so this learning rate is one that decays over time. By using such a learning rate, we get back exactly the sample mean. Remember, all we've done so far is basic algebra. Here's what it would look like if we translated it into our Monte Carlo reinforcement learning code to update Q. The new estimate of Q of SNA is updated as the old estimate plus 1 over n times the latest return minus the old estimate. Just note that the equal sign here means assignment. We're not saying that both sides are equal. The left side is the new estimate, and the right side holds the old estimate. We just haven't bothered to subscript them. However, we are not done yet, because we're going to make yet another modification to this. Remember that, in our latest value iteration loop, we are updating the same Q dictionary using different policies. this policy is being updated on each step. And therefore, the samples which we are using to calculate Q of SNA are not coming from the same distribution. In this case, we don't want to use exactly the sample mean. Intuitively, the oldest samples come from the oldest policies. They don't really matter that much. The newest samples come from the newest policies, and they matter more. The key is to use a constant learning rate instead of one that decays over time. Doing so gives us what is called the exponentially decaying average. The idea is, when you take the conventional sample mean, each sample is weighted equally. As we said, we don't want that because old values come from old policies, and so they come from a different distribution than the one we are now interested in. On the other hand, the exponentially decaying average weights each sample in an exponentially decaying fashion. The most recent sample matters most, and the weights for each sample decay exponentially as you go backwards in the order they were collected. So now we can express our value iteration code again, but this time we can fill in this little missing detail about how to update Q of SA. So this is the exact same pseudocode as before, except I've replaced the middle block of code with the actual update we can use to update Q. Unfortunately, at this point, there is a subtle but important detail we have yet to discuss. So we are not quite done specifying our algorithm, but we've laid out most of the groundwork.